This is Dr. Vamsi Mohan, Professor, Department of Civil Engineering in Institute of Aeronautical Engineering. So, today I am going to discuss about the section modulus for I sections, symmetrical and unsymmetrical, T sections and angle section. In the previous session, we have discussed about the definition for section modulus. Section modulus is a measure of the strength of the member. In other words, actually, it is a measure of bending strength of the member, which is given as the ratio of moment of inertia to maximum distance of fiber from the neutral axis. That is I by y maximum. So I by y maximum is the section modulus. So moment of inertia for different sections varies with the depth actually. As the depth increases, moment of inertia increases. And if the same area, for the same area BD, if the depth is increased and breadth is decreased so that the area remains same, in that case, say now call the dimensions are B1, D1. So here BD and B1, D1, area is same, but if D1 is greater than D, then the moment of inertia of this section will be greater than the moment of inertia of this section. Okay? It means the strength of this section will be more than the strength of this section. That is because of the greater value of moment of inertia. In the last session, we have seen about the section modulus for standard sections, basic shapes as rectangular section, solid rectangular section we have seen. So for this, the neutral axis lies at the middle because it is symmetrical. So distance of extreme fiber, maximum distance is d by 2. So the stress variation will be linear with maximum at extreme fiber. In this case, because of symmetry, negative and positive stresses, maximum stresses are equal. Okay. So the moment of inertia in this case is BD cube by 12, that is about centroidal axis, and y maximum is d by 2. So the section modulus will be I by y maximum. So that comes out to be BD cube by 12 divided by d by 2. So it is BD square by 6. BD square by 6. That will be the section modulus for solid rectangular section. Similarly, for solid circular section also we have seen. For solid circular section, the moment of inertia is pi d power 4 by 64 about centroidal axis. And extreme fiber distance in this case is d by 2 again, where d is the diameter. So y maximum is d by 2. So section modulus is I by y maximum in this case also. So it is pi d power 4 by 64 divided by d by 2. So it comes out to be pi d cube by 32. So this is the section modulus for a solid circular section. Yeah, these things we have discussed in the previous session. Next, For a hollow rectangular section, with external dimensions capital B, capital D, and internal dimensions small b, small d. Okay, a hollow rectangular section. And this is also symmetrical with extreme fiber distance being capital D by 2. Okay, and moment of inertia in this case is pi b d cube by 12 minus small b d cube by 12. Okay, so it is b by 12 into d cube minus small d. The moment of inertia is b by 12 into d cube, capital D cube minus small d cube. Okay, and the extreme fiber distance maximum, y maximum, is capital D by 2. Capital D by 2. So now the section modulus is I by y maximum, that is b by 12 into d cube minus small d cube divided by capital D by 2. Divided by capital D by 2. Okay. So this comes out to be b by 6d into d cube minus small d cube. This is section modulus for the hollow rectangular section. For hollow rectangular section, the section modulus is b by 6d into d cube minus small d cube. Okay. Next, for hollow circular section with outer diameter capital D and inner diameter small d. Yeah, for this section, the moment of inertia is pi d power 4, capital D power 4 by 64. This is about neutral axis, okay, centroidal axis, minus pi into small d power 4 by 64. That is the moment of inertia, and maximum fiber distance is capital D by 2 to the extreme fiber. Y maximum is capital D by 2. So the section modulus is I by Y maximum again. So pi by 64 into d power 4 minus small d power 4 divided by d by 2. So it comes out to be pi by 32d into d power 4 minus small d power 4. This is the section modulus for hollow circular section. Hollow circular section. Let us consider some common sections which are used in steel structures. They are symmetrical I section, unsymmetrical I section, T section, angle and channel sections. Okay, these are most often used in steel structures. So let us see how to find out the section modulus, because it is the measure of bending strength. And we have, okay, bending strength is, it depends on the section modulus. Okay, yeah, for the given permissible stress, the bending strength depends on the section modulus of the section. Okay, first let us consider the symmetrical I section. Let us take the dimensions now as say this is 100 mm and flange, bottom flange thickness say 10 mm, top flange thickness also is 10 mm, and web thickness is say 12 mm. Just for example, I'm telling. It may have any other dimensions. Okay. Yeah. Let the depth of web portion is 120 mm. We can take any other dimensions also, but how to find the section modulus? That is our problem. For that, first you need to locate the centroidal axis. Okay. First you need to locate the centroidal axis, and you find maximum fiber distance from centroidal axis. Okay. And then moment of inertia about centroidal axis. You need to find out moment of inertia and maximum fiber distance to find the section modulus. Okay. So for that, first you need to locate the centroidal axis or the neutral axis which passes through the centroid. Location of neutral axis. So for symmetrical sections, we can easily identify the location of centroid. Okay. Yeah, it is symmetrical about horizontal axis passing through the center. Okay. So it has two axes of symmetry actually. One vertical and one horizontal axis. So the point of intersection of this will be the centroid. Okay. So the neutral axis here lies at a distance of 10 plus 60, that is 70 mm from bottom and 70 mm from top. So total depth is 10 plus 10 plus 120, that is 140. So it lies at the middle. Being symmetric about horizontal axis, the centroid lies at the mid height, that is about 70 mm from base. Okay. It lies 70 mm above the base. So we can easily locate the centroidal axis for symmetric sections. If unsymmetric sections, then we have to find the location. We cannot readily identify the location of centroid. Okay. So you need to calculate the position of centroid for unsymmetrical sections. Okay. So for this case, the centroid lies at 70 mm above base. So Y maximum in this case is 70 mm. Y maximum is 70 mm. And how about the moment of inertia? Moment of inertia for this section about centroidal axis. About centroidal axis. So you can divide this area into three components: top flange, bottom flange. This is first part, and this is second part, and third part is web portion. So we find the moments of inertia of these three parts separately about the centroidal axis. Okay. For part 1, that is top flange, the moment of inertia about its centroidal axis, because the centroid of top flange and centroid of the entire section are different. Okay. So the distance between these two centroidal axes is say h1. What is h1 here? Is 60 plus 5. So centroidal axis here lies at the middle of this for this part. Okay. So 5 mm from top. Remaining distance from neutral axis is 65. So distance between the centroidal axis of part 1 and centroidal axis of the entire section is 65 mm. Similarly, the centroidal axis of part 2 and centroidal axis of entire section are also separated by a distance of 65, and centroidal axis of part 3, that is web, coincides with the centroid of the section. Okay, as a whole. So the distance h3 will be 0 because it is passing through the centroid of web. Okay, they both coincide, so distance will be 0. Now we apply parallel axis theorem to find the moment of inertia of this I section. Okay, what is parallel axis theorem? Moment of inertia about any axis is, for any given section, is moment of inertia about centroidal axis plus AH square. Okay, moment of inertia about centroidal axis plus AH square. That gives the moment of inertia of the area about any axis which is parallel to the centroidal axis and is at a distance of h. Okay, this is called parallel axis theorem. So for now, for part 1, top flange, okay, the moment of inertia about centroidal axis Ig will be BD cube by 12. Okay, for a rectangle we have seen already, BD cube by 12 plus area of the flange into h1 square. Okay, this multiplied by 2 because the bottom flange also is of same area and same is located at the same distance. So the bottom flange also will have the same moment of inertia as this. So we can simply multiply with 2 plus moment of inertia of web portion, that is directly obtained as BD cube by 12 because the centroidal axis coincide here, h is 0. Okay, so now what is the breadth of flange? 100 mm and depth of flange is 10 mm. BD cube by 12 plus BD. What is BD here? 100 into 10,000 into H1 is 65 square. This multiplied by 2 because we have two flanges of same area symmetrically placed about neutral axis, plus for flange area, for web area it is breadth is 12 mm into d cube 120 cube by 12 BD cube by 12. Okay, so this gives the moment of inertia of the section. Okay, so it comes about how much will it be? 8466 plus 1728000 plus it comes out to be 10194,666.6 units will be mm power 4. All the units are expressed in millimeters. Okay, so this is the moment of inertia of the I section about centroidal axis, and we know the maximum fiber distance, that is 70 mm. So the section modulus is now, section modulus is I by y maximum. Okay, so this divided by 70, so it comes out to be 145638.1 mm cube. Okay, this is how we find out the section modulus, which is a very important property for any section subjected to bending, because the bending strength mainly depends upon the section modulus. Okay, yeah. Next, this is for symmetric section. Let us consider now unsymmetric I section. Unsymmetric I section. So let the top flange be of dimensions 60 by 10 and bottom flange be 100 by 10 and web portion be of dimensions 100 by 10 again. Just for example, I am taking all these dimensions. Now, this is unsymmetric. It is clear from the figure, isn't it? It is unsymmetric about horizontal line. It has one vertical axis about which it is symmetric. So it is symmetrical about vertical axis. Only one axis of symmetry it has. So what can we say is the centroid lies about this axis of symmetry. At what height exactly from bottom or top we don't know. Okay. So first step is to find the location of centroidal axis. Okay. And one thing that we can say is this is close to the bottom flange because y dash y bar will be that is neutral axis is close to the bottom flange actually here because the area is concentrated more at the bottom. Okay, understand? So it will be nearer to the bottom flange. Neutral axis will be nearer to the bottom flange. So how to locate the centroid now? Neutral axis y bar. Yeah. This a1 y1 or sigma ay by sigma a. Okay. So here also we divide this into three components: top flange, web, and bottom flange. Okay. So for top flange, area is a1 and distance of centroid of this from bottom is y1. So we are locating distance of centroid from bottom edge. Okay. So we take all these distances y1, y2, etc. from bottom edge only. a2, y2 plus a3, y3 by a1 plus a2 plus a3. We can also write this as sigma ay by sigma a. Okay, it is clear. So this y1, y2, y3 are measured from bottom edge. Okay, and how about the centroid of web portion? It lies at its midpoint, at the midpoint of web. Okay, from bottom edge, its distance is taken as y2. Similarly for third area, y3. So here a1 is 60 into 10 and y1 is, what is y1? 10 plus 100, 110 plus 5, 115. This is mm square. Okay. Similarly, a2 is 100 into 10 again. A2 is 1000 mm square and y2 is 50 plus 10, that is 60 mm, and a3 is 100 into 10, 1000 mm square, and y3 is 5. Y3 is 5. Okay. Now we can locate, we can calculate y bar. So 600 into 115 plus 1000 into 60 plus 1000 into 5 divided by 600 plus 1000 plus 1000. Okay, this gives the distance of centroid of the given I section, unsymmetrical I section. Okay, so it comes out to be 600 into 115 plus 65,000 divided by 2,600. So it comes out to be 51.54 mm. Y bar is 51.54 mm. Okay, from bottom edge of the section. The location of centroid is 51.54 mm. And now once you locate this, then to find moment of inertia of the section about neutral axis, that will be the next step to find the moment of inertia, because we finally want the section modulus, which is given as I by y maximum. And in this case, y maximum will be the distance of top fiber. Okay, this is y bar is distance of bottom fiber from neutral axis, which is 51.54, and distance of top fiber from neutral axis, total depth is 120 minus 51.54, that is 68.46. 68.46 is the y maximum, distance of extreme fiber from the neutral axis. Okay, so I by y maximum gives section modulus. Okay, so y maximum we can find now, knowing the location of centroidal axis. Next is to find the moment of inertia of the section. So how will you get moment of inertia? Again by parallel axis theorem only. Okay, by parallel axis theorem we have to locate, we have to find out moment of inertia of the given section. Okay, yeah. For this also we can find out one by one the areas of top flange, web portion and bottom flange. Okay, so after locating this centroid, we find the 51.54 is the centroidal distance. So moment of inertia of the section now is, for top flange it is BD cube by 12 about its centroidal axis, plus area and h square. What is h square? So it is this distance h1. Okay, so the 68.46 minus 5, that is 63.46 square, plus for web portion, h2 will be this distance, centroid of this. Okay, so this is h2. So h2, how can we find h2? The location of the centroid of the web portion is 60 mm. Okay, from bottom it is 60. So 60 minus 51.54. Here you have to find h1, h2, h3 separately. h1 is y maximum minus 5, that is 63.46. h2 is 60 minus y bar, that is 8.46. Y bar is 51.54. Okay, and h3 for this portion, This is H3. It is y bar minus 5. So how much is 51.54 minus 5? So that is 46.54. 46.54. Now we will use these distances in the calculation of moment of inertia. So for A2 now, it is 1000 into for first it is centroidal moment of inertia we have to find out. How much it is? 10 into 100 cube by 12. Base is 10 for this web portion and height is 100. BD cube by 12 plus AH square. 1000 into H means here H2. 8.46 square. Plus for third component, bottom flange, area centroidal moment of inertia is first BD cube by 12 plus area 1000 into H3. H3 is 46.54. 46.54 square. Okay. So this gives moment of inertia of the section. So let us see how much it comes. So it is 5063.46 into 600 plus 5000. That is 2421303 plus this component. Next, this one is 8.46 square into 1000. It comes out to be 904,904.9. This component. Next, this component plus 46.54 square into 1000 plus 2174304. Okay. So by summing up all these three, so 2421303 plus 904.9. So moment of inertia comes out to be 5500512.8 mm power 4. So now the section modulus is obtained by dividing I by Y maximum, which is 768.46. Okay. So Z is now dividing with this is I value, dividing I with 68.46. That gives Z value actually. Okay. Yeah. This is the section modulus. 68.46. And units will be 80346.4 mm cube. Okay. So this gives the section modulus for given unsymmetrical I section. Unsymmetrical I section. So this is the way how we calculate the section modulus. Okay. So first step is to find the location of centroid. Okay. In calculating section modulus of any given section, first we have to locate centroid, center of gravity. Okay. If it is symmetrical section, we can readily locate. If it is unsymmetric, then we need to calculate. Okay. After that, calculate or determine the moment of inertia I. Determine the moment of inertia I. By locating centroid, you will come to know what is maximum fiber distance. Okay. And after finding out the value of moment of inertia, we can calculate section modulus as I by y maximum. Okay. Yeah, this is the procedure for calculating the section modulus for the given section. Okay. Now T section also we can calculate the same way. We can locate centroid first. Okay. In this case, the centroid is located nearer to the top edge. Okay. Nearer to the top edge, because most of the area is concentrated at the top. So centroid will be nearer to the top edge. So first you have to locate the centroid and then calculate moment of inertia about the centroidal axis. After that, the section modulus. Okay. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.